Hello friends, welcome to another video on UNET segmentation. In this video, we are going to use the derived dataset for Retina Vessel Segmentation. This complete program is built using the TensorFlow 2.0 framework. If you like to learn more about image segmentation, do watch the complete video and subscribe the channel. So without any further delay, let's start. So here we are in our Atom text editor with some Python files in it. So let's first start by taking a look at the retina blood vessel segmentation dataset. Okay, so here is the folder containing the dataset. So it contains two folders, training and testing. So let's take a look at the training. It contains three folders. First is the images. So these are the 20 training images. Let's take a look at the few samples. Okay, now it's the second folder is the mask. So this mask basically is the area on which the image is there, because in the image we have the eye, the useful data, that is eye, and the background region which is not useful. The third folder is the first manual, which contain the annotated mask, that is the retina vessel. So this is all about the training data set. The same is with the testing data set, but in the testing data set we have two annotated masks. First is the first manual and second is second manual. So we are going to use the first manual folder only. So the test dataset also contain 20 images. So both the training and the testing contain 20 images. So I know these 20 images are really less image, but as you can see, the annotation is not that easy part. Here it is really difficult to annotate such fine things. Maybe even some retina vessels are such fine that they can't be seen, so they cannot be annotated. But we have to use these 20 images only to work for the program. So what we gonna do? So first of all, we're gonna start with the data preparation and the data augmentation part. So we're gonna try to augment it and try to increase these 20 samples to 40, 60 or 80. So let's start with the code. First of all, we are going to import all the required libraries. First is the operating system, second is NumPy, third is a CB2, that is OpenCV. This is basically used to read and write the images. Next is the globe. Globe is basically used to extract all the paths for those images and mask. Next is TQDM. TQDM is basically a progress bar. While augmenting the images, we want to know how much the loop is completed and how much it is remaining. So it's basically a progress bar to just display on the console. Next is import IO, not import IO, image IO. This is used to read the GIF mask. So let me show you the mask. They are basically in GIF format. You can see .gif. To read those GIF files, we are going to use the image IO library. And the last is the augmentation library, which we are going to use to do the data augmentation. So here are some of the functions which we have imported from it. So these are all the libraries which we need, which we have imported here. So first we will start by creating a function called create_dir. So this function takes a path and create a directory if that does not exist. We are giving it a path parameter or argument, you can say. So we are going to first check if that path does not exist. If not, okay, os.path.exist. okay, I'm sorry for this silly mistake. If not, if that path does not exist. So if it's exit, then it's no problem. If it does not exist, then we need to create that path. So we're going to say os.make_dirs and give it the path. So this function is used to create the directory for us, because we are going to save our augmented images. That's why we need this function create dir. Next we are going to load the data set. both the training and the testing. Let's create a function called load data. It also going to take the path. Next, let's load the training images first. So here I have a way. So the images are going to be called X and the mask are going to be called the Y for easiness. So let me write it here. X equals to images and Y equal to mask. So it is true for both testing and training. So train X basically mean training images. So let's first join the path was.path.join. So we have some path, and so we are going to give it this path, this path, that is media nickel ml dataset, and then this retina blood vessel. This path we're going to give it, and for training images we're going to say training and then images. Okay, training, and inside it we're going to say images. And next, because we need to load all these TIF files, okay, so we're going to say star.tif. So we want to have the path of all the path which begin with anything but should end with .tif. Okay, now we have this path for the training images. Now we're gonna use the globe function. So globe helps to extract all the path with .tif extension. Now we're going to sort these paths using the sorted function. So like this we're going to extract the training mask and we're going to call them train Y. Let me copy this because it will be useful. So we're going to call it train Y. So instead of images we're going to say first manual, and the mask are in .gif format. Okay, so now we have both training images and training mask. So like this we're going to extract the test images and test mask. Let's rename them, call them test X and test Y. Okay, now instead of training we have to call it test. As you can see, the folder name is test. So this is test. Now let's return them, train X and train Y. Okay, then we can see test X and test Y. Okay, so now we have the function called load data, which takes the path and return the training images, training mask, test images and test mask. Okay, now let's move to our main function and start calling these functions. So let's seed, use seeding first. Now we are going to load the data. Okay, so first we need the data path. So we have this data path. Now we are going to say is equals to load data, and we're going to give it data path. Okay, so now we're going to check the how many images and masks are there for both the training and the testing. Train, so let's say length train X and same length train Y. Okay, and same we're going to do for the testing. Test X and test Y. Okay, now we're going to print it and check. Name of the file is data. So you can see the training contained 20 images and 20 masks, and test also contained 20 images and 20 masks. Okay, so now we are going to apply data augmentation on the training part. So we need to create some directories. So let's say creating directories. Okay, incorrect spelling, DIORIS, creating directories. Let's call that function create dir. So we're gonna call that folder new data slash train slash image. Okay, and next folder for the mask. Okay, we're going to create two more folder for testing, but in case of testing we don't provide use data augmentation on them. We just going to resize them and save them. Okay, so don't worry about that. Why are we creating testing folder also? We just going to save them in a proper format like in PNG or JPG, because some images are TIF, some are GIF, so this is not a proper format to work with. We are going to save them like JPG or PNG, so that it is easily readable with single OpenCV library. Okay, now let's create a new function called augment data. So first of all, it take the images path, then mask path, then where the augmented or the images are going to be saved, and next is a boolean parameter argument. We're going to say it to true now. So if argument is set to be true, this means apply data augmentation on both the images and the mask and save them. And if it is if argument is false, just resize the image and mask and save them in the save path folders. Okay, now we're going to say size. Okay, size basically means what is the size which we are going to use for this whole project. Okay, we're going to provide it in the input image, the models, everything. So we're going to say we are going to resize the images to 512 by 512. Okay, for idx, then x, then y. Okay, we're going to say enumerate, and inside we're going to say zip, because we have two things, images and mask, two lists. That's why we need to use a zip function. Then we need to use a progress bar here for easiness, because the loop runs maybe for 10 minutes but we don't see any progress, so it just don't feel good. That's why we use progress bar, so that we can see there's some progress. Okay, so now we have this loop. Next we're going to extract the name. Okay, because we are going to save the image. Okay, the image and the mask, the augmented, non augmented, we need a name. Okay, a common name for both image and the mask. So let's say we have an image at index 0 and a mask at index 0, so we're going to same that with the same name, same extension, so that it is easily readable. Extracting name. You can also extract extension, but extension we are going to use our own, that is JPG or PNG. So we're going to say name is equals to x dot split this slash. Okay, so let me print the x first, x and y. Okay, and then run it. So we're going to say break here. Let's go below. You can say argument data train x. Okay, train y. Okay, save path is new data slash train. Okay, and argument is set to be true. Okay, now let's run it. Okay, we have some issue here. Okay, there's a mistake. It should be for idx comma x comma y in tqdm, then enumerate, then everything else. Okay, so we have the path. This is the complete path for the image, and this is complete path for the mask. So we need to extract this 21 underscore training. Okay, we need to extract this string. You can also extract this from, or you can choose any just a common. It should be common for both training and testing. Okay, so let's extract this 21 underscore training. So you can see the entire path contains slashes. So you can copy this slash and we're going to split it. That's why I already use this slash here. Okay, now we're going to print name. So this split is going to create a list. Okay, let's remove this from here, X and Y. So you can see it has created a list. We need 21 underscore 1. So we need to extract this last item from this list. So we're gonna say -1. Okay, now we know that this is the name. We need to extract this name, so it is before the dot. So we're gonna split it again on the basis of this dot, and we're gonna print it. So you can see now we have split it on the basis of this dot. So we have the name at the index 0th, and on index 1 we have the extension. So now you have both the image name and the image extension. So we need only image name. We're gonna say 0. Let's print it again. So we have the name. Okay, so we have successfully extracted the name. Now we are going to read the image and the mask. So let's say X is the image. So we're gonna say cv2.amRead X, and cv2 dot, we're gonna read it as a grayscale, not a grayscale, RGB image. We're gonna say I am read color, and like this we're gonna read the mask. It's a, the mask is a GIF image, so we're gonna use image IO dot m I am read Y, and we're gonna say 0. So let's print this shape. Okay, so you can see the shape 584 by 565 by 3. This is the shape of the RGB image, and the shape for the mask is 584 by 565. Okay, so we have successfully read the image. So let's write a comment here, reading image and mask. Okay, so now we need to apply data augmentation on these X and Y. So we are going to apply data augmentation only and only if argument is set to be true. If argument is equals to true, we need to apply data augmentation. Let's say pass. Now else, we're gonna work on else condition now. First of all, else augmentation is false. So what we gonna do? So we are only going to resize them and save them. Okay, so we have created a list called X and Y containing the X, basically small x, that is the RGB image, and small y, the RGB mask. But if this X is here, so we're going to apply some data augmentation here, and this list would be like X1, X2, and here it would be like Y1 and Y2. So I want to have a common list, common name for both, if augmentation is there or augmentation is not there. Okay, now we have the data here in this X folder. So we're gonna resize it now and save it. For I comma m, I comma m means image and mask in zip capital X comma capital Y. So again a loop here. So let's resize them. I equals to cv2 dot resize. You're gonna say I and then the size, that is width comma height, and mask is like cv2 dot resize. Again instead of image we're gonna write mask here, and we're gonna say width comma height. Okay, we also need to give it a name. We have the name. Okay, we need the path. If length of X is 1, okay, then tmp image name is equals to you can say name dot jpg. Okay, and same for the mask, tmp mask mask name is equals to f name dot jpg. Okay, so if length is 1, but if length is not 1, we have applied data augmentation and we have multiple images here. So what we gonna do, because if we use this, then every image would have same name, so we need an index variable for index 0 else let's copy this. It's just going to be a little different, not much different. So we're gonna write an index variable in front of it. Okay, so now we have the names and the extension ready. Now we need image path os.path.join. So we're gonna say save path, then image, it should be image, not u image, u is done by mistake, and then tmp image name. Now for the mask, same thing, mask path is equals to os.path.join, then we're gonna say save path and mask, then temporary mask name. Okay, now we're gonna save it. cb2.imewrite image path, and we're gonna say I cb2.imewrite, and we're gonna say mask path, and we're gonna write m here, and we're gonna increment the index. Okay, so let's do it for both. Let's do it for the training images only now. So we move to the, so we have new data folder, and we're gonna delete it, and we're gonna run this program. Okay, I know what I have to remove. This break statement we have to remove now. Okay, so we have some issue here, local variable x referred before assignment. So let's check what the issue is. Again, let me just check it and see what the issue is. So I know what the issue is. We have to say argument is equals to false, and I'm just checking what the issue is. Okay, so you can see the progress bar is working fine. We can easily see how much the images are done. So just take 1 second, and the both the training image and mask should be saved here, and they are resized. So you can see we have the images. Let's see their property. So name is like 21 underscore training dot jpg, extension is what we have done, and they are resized to 512 by 512. So they are jpg images. There are 20 images. Let's check. So there are 20 items, so 20 images, correct. Now we're going to check for the mask. So mask is also like jpg images, image slash jpg and dot jpg, and size is like 512 by 512. You can see the thing worked fine till now. Now we have to do the data augmentation part. Okay, let's delete them and write the code for the data augmentation, where we have set argument to true. Let's use the break statement here and move to this part where if argument is equals to true, set is true. Okay, so we have various functions above. We have called the horizontal flip, vertical flip, plastic transform, grid distortion, optical distortion, coarse dropout. So there are more data augmentation functions. I've just called these only. So I don't want to apply more heavy data augmentation, because the training needs, then images would be more and it would need more training. But for this demonstration purpose, I'm just using small data augmentation techniques only. For you, you can try more. Horizontal flip. So it has a variable or parameter called p, basically means probability. What is the probability of applying an image, applying the horizontal flip to the input image or mask? Okay, so we're going to say to 1.0, apply it. There should not be any chance that it is applied or not applied, just apply it. So augmented is equals to AUG, image equals to X, and mask equals to Y. Okay, so we have X1 equals to augmented image and Y1 equals to augmented mask. Okay, it should be in quotes. That's my mistake. Okay, so you can see now we have X1 and XY. Let's copy it these X and Y variable from here. So now we have X1 and Y1 here. Okay, so now let's do one thing. Let's run this part only so that we can check for error or any other thing. Okay, so it has run because we have used the break here at the last. So only one image is done. So we're gonna check it. Okay, so there are two images here. So this first with the 0_0 here _0 jpg is original image, and second is the horizontal flipped version. Okay, and same is to be done with the mask. You can see this is original mask and this is horizontal flipped mask. Okay, now let's apply more data augmentation technique. Let's remove this folder. Okay, so like this you can do vertical flip also. Let me copy it because there's a just single thing change. This is vertical flip, and instead of X1 and Y1 we're going to say X2 and Y2. We're going to add X2 and Y2 to the list. So this is a simple offline data augmentation technique. I would add more here. Let me just paste the code directly. Let's add it X3, X4 and X5. Okay, here Y3, Y4 and Y5. Okay, so now let's run this complete code. Not complete, let's just run it for one image only and see the newly formed images. So this is original image. No, this is not original. Let me just reload the entire folder. Okay, so you can see this is the origin because it contains the 0 index number. This is horizontal flipped image, this is vertical flipped. Now here it has applied plastic transformation. Next, this is grid distortion, and this is optical distortion. So these are the 5 data augmentation technique which we have applied here. So you can say we have used one image, the original image, and converted it into 5 different images. Okay, so in total we have 6 images. Okay, now let's apply it to the entire data set. Let me remove it and also apply to the test data set. Let me copy it from here, but on the test set we're going to set argument to false. I'm going to say test X and test Y. Okay, now let's run this data augmentation part. Okay, so both training and the testing data augmentation is done. Now let's check how many images are formed. So let me reload it. Sometime it don't work. So you can see 140 images. Okay, 140 images is nice. Okay, it's taking time. So you can see a few samples. You can see these images, different data augmentation applied. So that's also, these augmentation are also applied to the mask. Okay, don't worry about that. These won't be applied to mask. They are applied both to the same image and the same mask. Now let's go to the test. Okay, I have got an issue, and what I have not changed is test. That's why it is 140. I think it should be 120. Okay, that's my mistake. I'm sorry for that. So let's do it again. So mistake are just a part of your life. If you don't make mistake, you aren't trying anything. So now let's check. Okay, let me reload it again. So this time it's 120 items. correct, because there are 20 images and we are converting it 6 times. So 6 to the 12, so it is 120. Okay, so now let's move to the test. E should be 20, okay, 20 items, and in the mask it's 20 items. Okay, you can see 20 images and 20 masks. So that's about the data augmentation part. So we have finished with the data augmentation and data processing part here. Now we're going to move to the UNET architecture. I already have a video on UNET architecture, but still we're going to start it from the scratch. Let's start by building the UNET architecture now. So I have imported all the libraries functions which we require. So UNET basically is an encoder decoder architecture. So it contains 4 encoder part, a bridge connecting the encoder and the decoder, and 4 decoder part. So both the encoder and the decoder and the bridge contain a convolution block which contain 2 3x3 convolution, each followed by ReLU activation. So let's build the convolution block first. So convolution block take the input feature map and the number of filter inputs and num filters. First is the convolution layer. It take number of filters. The kernel size is 3x3 and padding remains the same. Next, we are going to insert the batch normalization in between the convolution and the ReLU activation. Next is again the ReLU activation. ReLU is one of the most used activation function in the hidden layers. It is really fast and easy. So again, we will copy this and repeat this block again, but input is going to be X. So this is our simple convolution block. What it has, 2 3x3 convolution layer, these two convolution layer, each followed by a batch normalization and a ReLU. Okay, now we start with the encoder block. Encoder block again takes the same, the input feature map and the number of filters. So encoder block is basically convolutional block and max pooling. Inputs and number of filters, and next it is followed by the pooling, max pooling, basically a 2x2 max pooling. Input is the output of the convolution block and it returns X, that is the output of the convolution block, which also act as a skip connection for the decoder block, and P, the output of the pooling operation. So let's build a function called build UNET and start building the UNET architecture. It take input shape as the parameter. Now first we're going to build the input layer and we call it inputs. Input. Okay, and it take the input shape as the parameter. Now let's build the 4 encoder block. So we're going to say S1 and P1. S1 is basically skip connection and P1 is the output, the pooling block. And we're going to say encoder block inputs and start with 64 filter channels. S2 and P2 is encoder block and the input is P1, the output of the previous max pooling block, and number of filter doubles from 168 to 128, not 168, it's double from 64 to 128. Next is S3 and P3 and input would be P2 and number of filter 256, and like this we have S4 and P4, the 4th encoder block, and in between we have the bridge connecting both the encoder and the decoder. Okay, now it's time for the decoder block. The decoder block takes the skip connection also, all in also from the encoder block. This skip connection helps in better propagation of gradient, and also it helps in the in bringing the information from the encoder part to the decoder directly. So let's build the decoder block. We take the input feature map inputs, then it takes skip connection feature, let's call them skip features, and then it take number of filters. Okay, so first in decoder block, first it is followed by 2 by 2 transpose convolution. First is the number of filters, then a 2 by 2 kernel size. Stride is going to be 2 because we want to double the resolution. Padding is the same, and input is the inputs. Next, we're gonna have a concatenation operation with the transpose convolution feature map and the skip connection. Concatenate. Okay, so here we have the X, the output of the transpose convolution, and the skip features. They both basically have the same shape, so it is mandatory to have same shape, that is same height and width for both the X and the skip features. Next, it is followed by the convolution block, that is X, the concatenated feature map, and number of filters. Okay, now we're going to return the X. Okay, so decoder block is complete. Now we're gonna have 4 decoder blocks here. Let's say D1 is equals to decoder block. Okay, first it take the B1, then it take S4, that is skip connection S4, that is the last encoder block, and 512 as the number of feature channels. Like this, it's gonna have 3 more decoder blocks. Okay, so decoder is now complete here. So after decoder, it is followed by a 1 by 1 convolution layer. We're going to say outputs equals to convolution. The output number of channel is 1, as we are doing a binary segmentation, and the kernel size is a 1 by 1. We're going to say padding equals to same, and activation would be sigmoid, as we are performing a binary segmentation. Activation is sigmoid, SIGMOID. Okay, and the input for this layer, output layer, is D4, that is output of the last decoder block. So we're going to build a model here. Model is equals to model class, and you take input layer, the output layer, output, and we can provide it a name, let's say UNET. Okay, now we're going to return the model. I make a lot of spelling mistake because my keyboard is new and I'm not adapted to it so much. That's why I'm having some issues sometimes with spelling mistakes. So here we call our main function. First is the input shape. We will have an input shape, and we have if input shape of 512 by 512 by 3. Now we're going to say model is equals to build UNET input shape, and we're going to call model dot summary, and we're going to run it. So let's run it and see if it works successfully or not, or it had some issue. Okay, so you can see it works successfully. So we have a total this much amount of parameter, and these are trainable, and some of them are 11,000 are actually non-trainable. So these non-trainable parameter basically come from the Bayes normalization operation. Okay, so you can see this is the entire summary. Let's go to the input layer first and check its shape. So you can see the input layer shape is 512 by 512 by 3, and it goes through all the encoder, bridge, and the decoder block, and give us an output with the shape of 512 by 512 by 1. 1 here is the number of class which you can decide. Here we are working with a binary segmentation problem. So output number of channel would be 1 with sigmoid activation. Always remember, with binary segmentation, number of classes would be 1 and output would be sigmoid. Sigmoid basically output a value between 0 and 1. Okay, so 0 and 1, it can be, if the pixel are close to 0, so the value of the output would be close to 0. It would not be perfectly 0, it would be near to 0, let's say 0.001. Okay, and the if pixel value is 1, so the value would be near to like 0.999 or 0.87. so in that case we're going to use a threshold, let's say 0.5. so if value is greater than 0.5, we can say it is 1. If it is less than 0.5, we can say it is 0. So like this we classify the output of the sigmoid into 0 and 1 category. So that's all about the UNET architecture. But still you want to learn more and see more videos, then check the I button with more UNET videos. I have a lot of videos on pre-trained UNET architecture where I have used pre-trained encoder like VGC 16, VGC 19, ResNet 50. You can watch that videos also and work with those models also. Now till now we have processed the data, augmented, we have the UNET architecture. Now we're going to start working for the training part. Let's start with the training part now. As we have the data ready, we have the UNET architecture. Now the next step is the training. First of all, here we are going to import all the required libraries. So let's we can copy some from here. Libraries. Okay. Okay, so before that, let's do one thing. os.by. So we're gonna set all the error messages, not the error messages, the messages on the console that is given by TensorFlow. So these are basically the messages given by TensorFlow. So I don't want these messages. So that's why I'm saying this. So I'm adding this line. So next we need the globe. Okay. Okay. So we need the globe to extract the images and the mask from this new data directory for both the training and the testing. We need to shuffle the training images and masks. So we are importing this shuffle function from the sklearn library. And we need a whole lot of things from the TensorFlow. So first of all, let's import the TensorFlow STF. Next, we need some callbacks like saving the model. We need to save the model. We need to reduce the learning rate at appropriate timing. Next is the optimizer. So for optimizer, we are going to go for the Adam. Next are some of the metrics like recall and precision. Okay, I have other matrices which I've already defined. That is IOU, dice coefficient, and dice loss. So we are going to call that also, and we are also going to call the build unit function. Okay, so these are all the functions and classes which we require here. So first of all, we're gonna define the height and the width here at the beginning of the code, because it is going to be used anywhere. It can be used anywhere, so we are defining at a global level. So we need this function also, so we're going to copy it instead of importing it. I prefer to just copy it. Okay, now let's go slowly in a sequence. Okay, so we start with the main function first. So first of all, we start by seeding the environment. np.random.seed, let's say 42, and same we do for the TensorFlow. ef.random.set seed, and we're gonna say 42 here. Okay, so during training, some of the files are going to be saved, like weight file and the CSV file. So for that, we're going to save those files in a specific directory only. So we're going to create some directory. So we're going to say create dir, and we're going to say file save. Next, we're going to define some hyperparameters. So first is the batch size. As I am using a GTX 1060 GPU with 6 GB of memory and with a image size of 512 by 512, So my GPU is going to support a batch size of 2 only. So let's define it 2, and maybe I have to reduce it to 1 also, because I don't know how much it's gonna support, but I am at least confident that 2 is the 2 it can support. Next is the number of epoch. You can say 200 or 100. Let's say 100 here for now. Okay, so we need to define some paths also. Say model path. So model is basically an H5 file which saves basically the entire model, its weight, the trained weight. Okay. We're gonna say os.path.join. First is files, next is model.h5. So at this point the files folder is created, so we can save use this files folder. Next is a CSV path. It basically going to create a CSV file which save the training loss and the other matrices like dice, IOU, recall, precision. Okay, this is basically just to see after the training is complete or during the training how much the values are. We can also plot graphs, okay, using this CSV file. So hyperparameters are complete. Next we need to load the data. We're going to work with a data set now. So data set path, so you can say data set path is new data. Now the train path and the valid or test path. So we can say train path is os.path.join. So first is dataset path, then it is train. Next is valid. Now here the test set is going to be used as valid on valid data set only. So we're going to say valid path is equals to os.path.join dataset path, and next is the valid. Okay, so paths are ready. So next we need to load the data. Now for loading the data we need to write a function to load the data. So let's write that function here. Def load data paths, and we can say x as images, or you already know, and y as mask. So we're gonna start with the path os.path.join first path, then image folder. Now inside image it contains jpg images, so star.jpg. Next we're gonna have the globe function, and after that we have sorted. Okay, now we're going to provide the appropriate brackets, and same for the mask, just changing the folder and the name from x to y and images to mask. So we have loaded both image and mask. We're going to return x comma y. Let's write one more function called shuffling. It is going to shuffle the image and the mask, that especially the training image and the mask. X comma y, shuffle x comma y, and random state to 42. Now we're going to return x and y. Okay, spelling mistake, no issue. Now we have this load data function, this shuffle function. Let's now move again to the bottom part and load the data, the train x and train y. It's like load data, the train path. Okay, now we're gonna shuffle these training image and mask. Shuffling, and we're gonna give it the training images and then training mask, that is training x and training y. Next we're gonna load the valid x or test x. Here we're gonna call it valid x. You can say load data and valid path. Okay, now let's print how many images are there, like we printed during the data augmentation part. frame length train x, and like this we're gonna then length of the train y, that is mask. Now same for the valid part, the validation data, we're gonna call it valid, and we're gonna copy valid x, paste it here, again paste it here, and valid y, copy and again paste it here. So let's do one thing, let's run till here and see if there's any issue or any problem till now. Okay, it has issue with the valid one. So we can see, okay, it is not valid, it's test. Okay, that's a silly mistake, I know. Okay, now let's again check it. So you can see in training we has 120 images and 120 masks, and in validation we have 20 images and 20 masks. So we're going to train it on 120 images and validate it on 20 images. Okay, so let's start now with the rest of the code. So now we need to set up the data pipeline. For the data pipeline we are going to use the TF data API. So let's start by writing some of the basic functions like reading image and reading mask. So first of all, let's write these functions. It is read image, it take the path. Okay, now we're going to say path is equals to path dot decode. We're going to write decode here because this function is going to be used inside TensorFlow and is going to encode that path, and I know it, so I'm specifically writing first here. But in normal condition path is generally a decoded one only, so it's not encoded. But as we're going to use inside TensorFlow, that's why I'm writing this line. X is equals to cv2 dot I am read, not I am write path, and we're going to read it as a RGB. So we're going to say cv2 dot I am read color. Okay, now the images are already resized, so we need not to resize them again. They are already resized to 512 by 512, but if you want to resize them to 256 by 256, so then you can write this function cv2 dot resize. You can say x, and here you can write width and height, but you can say at above we have specified we're going to use 512 by 512 size, not the 256. So we can remove this line, or let's comment it out now. You can say x divided by 255 for the maximum pixel value. So here we are normalizing the pixel value in the range of 0 and 1 by dividing the pixel value, whole pixel value, with the maximum pixel value, that is 255. Now we're going to say x is equal to x dot ast by pe, changing it to float 32. We're going to return x. Okay, now we're going to read the mask, giving it the path. Again we're going to decode the path. Let's say path is equals to path dot decode, as this function is also going to be used inside the TensorFlow. And here we're going to read the mask as grayscale. And to read it as a grayscale, we're going to say cv2 dot I am read underscore grayscale. Okay, now again the resizing thing. Okay, so the resizing thing is common. If you want to resize, you can uncomment this line, and here it is, normalizing it. Okay, so again we are converting into float 32, but we're also going to extend its one of its dimension, because still here, because actually if you read it as a grayscale, it will give you, it won't give you any channel, it just give like 512 by 512, but we need image in the format of 512 by 512 by 1. That's why we need to expand this dimension on the last axis. So we're gonna, so here it's going to be like 512 by 512 by 1, and we're going to return x here. Okay, so that's done. Now we're going to create a tf parse function. What it take is a single image path and a single mask path. So x and y basically are single image and mask path, not a list here. Okay, So let's define again a function called parse inside this tf parse function. Again, you take the x and y, the single image and the mask path. So we're going to read the image and mask here in this underscore parse function. X is equals to read image. So here you can see we are using both the read image function and the read mask function. And it's going to read on x and y. Now here, as we are using a function which is outside the TensorFlow, we are using OpenCV NumPy library. So we have to use this function. So for using this function inside the TensorFlow, we have to use the tf.numpy function. tf.numpy function. Okay. Here we have to write the parse, that is the name of the function first, is parse. And next it take the x and y, that is the input. And next we have to give the data type for the output, that is these x and y. These x and y are in float 32. So we're gonna say tf.float 32. Now it's returning the x and y, the image and the mask array. And we also need to provide the shape for them. What are their shape? So we know it's height, comma width, comma 3. And for mask it is y dot set shape. And okay, for the mask it is height, comma width, comma 1. Oh. Okay, so now we need to write one more function. This is basically the main function which we are going to use directly the below. So this is tf dataset. We're going to give it x and y. X and y here refer to the list, basically list, or you can say the capital X and capital Y batch size. So don't confuse them here. It is small x and small y. Basically it is list of images and this is list of mask that we have loaded here, that is train x, train y, valid x and valid y. And batch size, let's say by default it's 2. Okay, now we're going to use tf.data API. Dataset is equal to tf.data.dataset. Then we're going to say from tensor slices. And we're going to give it a list of, no, not a list, a set of x and y. Okay, it should be capital X and y. Next, then dataset is equal to dataset dot map. And we have already written the function for map, that is tf parse. Okay. Now we're going to say dataset is equals to dataset dot batch, and we have a batch size of 2. Next, dataset is equals to dataset dot prefetch. You can say prefetch, let's say 4, and we're going to return the dataset. Okay, so the dataset part is done. Now let's move below and complete the rest of the part. So we're going to say train dataset is equals to tf dataset, and we're going to provide the images train x, train y, and batch size would be equal to batch size. And same we're going to do with the valid dataset is equals to tf dataset valid x, valid y, and again batch size is equals to batch size. Okay, now we need training steps for these. So how that is training steps basically means the steps, training step and validation valid step basically mean the number of batch. Okay, so let's say you have 10 images, okay, and you have a batch size of 2, so you have 5 batches each of 2. So these are like 1,2. The next batch would be like 3,4. Then you have 5,6. Then you have 6,7. Then you have 7,8. Okay, so like this 1 2 3 4 5 6. Okay, it's repeated. I've done it incorrectly. It should be 7 8 and then 9 and 10. So this is how you divide. So this is how it divides. So these are 5 batches. Number of batches is 5. So, or you can say the number of steps is 5. So we need the train step is equals to say length of train x divided by the batch size, and that's how we're going to calculate the valid steps, and say length of valid x then batch size. Okay, now what happen if the batch size is not properly divisible by the batch size? Then we're gonna have some more thing. If length of training x, okay, I'm sorry for these mistakes, and modulus with batch size is not equals to 0. If the remainder is not 0, then we can say train step plus equals to 1. And same for the validation. Let's copy it. It's easy. We copy and then do it. So instead of training as x, we need valid x. Batch size remains the same, and we need valid steps. Okay, so it is done. We have the steps ready. Now let's come with the model part. So the data set is done. You can see from the beginning we have just read the data from the folder. Then we have load the paths. Then we have the TF data API ready. Then we have calculated the number of training steps. Now it's time to load the model. You can say model is equals to build unit, and what you take the input shape, height, width, and the number of channel, that is 3. So next we need to compile the model. We'll say model dot compile loss is equals to dice loss. Then optimizer, you can say optimizer equals to Adam, Nella, learning rate, and matrix. So we can have matrix like dice coefficient. We have already defined them above in the matrix.py library. IOU, recall, we have imported it above. Then precision. Okay, so we've compiled the model. Now let's say model.summary. Let's check it here. If till now it's working or there's any issue. Okay, batch size is an issue. Batch size is not defined. Okay, the spelling mistake is there. BATCH. Now again it's incorrect. It should be BATCH, not the. Okay. So there's some issue with like this TF map. Okay, let me check what I have done. Okay, now I know what the mistake is. I haven't written anything from a x comma y. It should be like that. So let's run it now. And okay, so you can see till now it's working again. We have the model summary. So let's go to the bottom part and complete the rest of the part. So now we need the to import all the callbacks. So callbacks are basically the piece of code that would run during the training. Okay, like saving the model or reducing learning rate and logging all the data. So that's what is callbacks about. First is model checkpoint. We take model path which we have defined during the hyperparameter. You can see this is model path, and it also has CSV path which we are going to use now. After this, verbose to 1 and save best only equals to true. Next is reduce LR on plateau. Okay, so this is basically used to reduce the learning rate. Monitor is equals to validation loss. So it will monitor the validation loss, and we're gonna set a factor. Let's set the factor. So what factor we're going to reduce the learning rate? We're going to, factor is 0.1. And patience. Patience is basically, so it will monitor a metric, that is validation loss, and it will reduce the learning rate with a factor of 0.1. So but after how many epochs? So let's say if I set to patience to 5. So if 5 epoch, in 5 continuous epoch, the validation loss does not decrease, it will reduce the learning rate with a factor of 0.1. Okay, so after patience we need to define the minimum learning rate. It should not go on and on and on reducing learning rate. It should not go below like 1e minus 6, or you can set it to yourself verbose equals to 1. Okay, so this is about the reduce LR on plateau. Next is CSV logger. So it basically logs all the data, that is training loss, that the dice coefficient, the IOU recall precision, everything for both the training and the validation. We need to provide the CSV path. Next is TensorBoard. So you can also log all the data in that TensorBoard for the easy visualization. And the last is early stopping. So early stopping is basically used to stop the training when the model starts overfitting, or we can say when a specific metric stops improving. So here the metric is validation loss. So when the validation loss stops improving for a specific number of patients, and that patient's value here is 20, then we're going to say 20. So if continuous 20 epochs, the validation loss does not decrease, so just stop the training, or you can say 10 here. It's up to you. I generally set it to high if my system is good. Let's say I'm training on a server or a cloud, then I set it to high. But if I'm training on my system, on my home system, then I set it to low. And restore best weights set to false. Restore best weights to false. Okay, so this is all about the callback. Now we have to just write the last function and the training will begin, that is model.fit. Okay, so first we're going to provide the training dataset, then the number of epoch, num epochs, then validation data, and we're going to give it valid dataset. Next is step per epoch, steps per epoch, and here we're going to provide the training steps, the train steps. Next are the validation steps, and we're going to say valid steps. Next is the callback. Okay, so that's all about training. So let's start the training now and see how much time it would take. Okay, so you can see the training has begun. It would take like 30 seconds for one epoch. Actually, I've already trained this model, so I'm not going to train it enough, and I'm going to copy paste those weights only. But let's do it for one epoch here, and then I'm going to copy paste those weights. So you can see the loss is already on 0.69, the dice is like 31, IU 18. Okay, so this is complete. Now it's doing for validation, so let's stop it. Okay, let's go above. Okay, so here you can see the loss is 0.65, dice is 0.34, IA 0.21, recall is 6.1, precision 4.4. So like this, there are other values for the validation. I need to have saved all the data in this files folder. Okay, and logs, the TensorFlow logs here, and rest of the things. So I'm going to delete these files as I've already trained it. So I'm going to copy that part, not the spy cache. So I'm going to paste them here. Okay, so let me show you the training now. The CSV file, so you can see. Okay, let me just go back. See, it is trained on 42 epochs basically. So I've trained it on 42 epochs, and let me show you the graph for the loss only, the loss, and comparing with the validation loss. Create this chart, a line chart we need. So you can see the blue one is the training loss and the orange one is the validation loss. So you can see how the training has gone through these 42 epochs. So now let's close it, don't save. So this is all about the training. Okay, so like this, that we train the entire model for a huge number of epochs. So I have trained it to 42 epochs, so I'm going to get decent performance, not that state of art and not that even bad, so that we cannot even see that if it is trained or not. It's just an okay performance. Okay, as my system is also not that good, so support my channel, subscribe it, and also join the channel, that is the membership, support it more. But for now, let's move to the evaluation part now, because the training is done. I have explained every part, how it is done. I have written it well. And now let's move the evaluation part, because evaluation is important. Okay. So what do we do in evaluation? We just take the test set and make the prediction and compare it with the ground truth mask. Okay. And using various matrices, just see how much good it has performed. Okay, now we're going to import some library. Let's do them from training. Okay, now we have imported CV2. Now we're going to import the TQDM, that is the progress bar. Next is TensorFlow. Okay, now we also need to load the model. So we need the custom object scope function, and to measure the score, the performance, we need different metric, and those metric are going to be taken from sklearn.model sklearn.metric class. So we're gonna measure the accuracy, f1, jacquard, precision, recall. Okay, and we need the functions from the metric class, metric file. So again, here we're gonna define the height and the width. I'm sorry for that. So let's copy some function from here. Okay, let me paste it here. Something I are going to repeat. So I'm going to copy them like this: read file, not read file, read image and read mask. So we need to just make small changes. Just remove this decode part. Okay, so again we don't need to resize them, they are already resized. But what we gonna do here, we gonna take one more thing here. Let's say ORI x to x. This is before the normalization. Okay, and like here we're gonna say ORI x is equals to x. So I'm gonna return ORI x, and I'm going to tell you why I'm saving this ORI x and the ORI and the thing here. So this ORI x is going to be saved, okay, on the disk. So we're going to visually see how the image look and how the mask look and how the prediction mask look. Okay, so next function we need is the load data. Where is the load data? Okay, here is the load data function. Okay, so we have this load data function ready. Now let's start with our main function and loading the data, loading the model, that part. Okay, so first of all, we're gonna create a folder to save our result. In this folder, create dir results. Okay, now I'm gonna load the model. So we have loaded this custom object class, not a class, it's a function. I think maybe it's a class, I don't know, so don't go in that. And we need to specify the function, that is IOU, the matrices which we have used here, which are not there in the TensorFlow. So we have used some matrices. Where are they? So there, here, there they are. Dice coefficient, IOU, and the dice loss. So these are defined in the matrix.py. So we need to provide them in the custom object scope function. Next is dice coefficient. And the serial order is not important. You just need to define all the external libraries which you have used. Now we can say model is equals to tf.keras.models.load model, and the model is saved in file slash model.h5. Okay, now we have load the model. We're gonna call it summary to check how it is working. You can see the model summary is there. So model is loaded successfully. Now we're gonna load the data. So we're going to load the test data sets. First is the dataset path, that is host.path.join new data, then it is test, and test x and test y. You want to say load data and give it the test dataset path. Okay, now we have loaded the training images and mask. Now we're going to make the prediction, and calculate the metric values. Different metrics we're going to use. First of all, let's say x comma y in tqdm, that is progress bar, zip test x and test y, and total is equals to length of test x. Okay, so first of all, we're going to extract the image name. Okay, so we're going to say name, and I only explained how it worked. X dot split slash -1. I'm just able to do it in my mind only, so I don't need to see it. But still, we're going to print the name and check for any error. We're going to break it here. So let's run it and you know, see the name of the test. Okay, you can see _01_test. Okay, so that's right. You have the appropriate name. Now we're going to read the image and mask. So we're going to say ORI X read image, then ORI Y, then Y. ORI basically means original image and original mask. So that's why ORI mean, it's not origin. Origin also means original. Okay, so we have loaded the image and the mask. Okay, now we're going to make the prediction. Okay, so we can say ypred equals to model dot predict. Okay, so what we're gonna need is expand the dimension of the input x on the axis 0, because here, let me give you an intro. The shape is like 512 by 512 by 3, and we need to convert it to 500, not like this, 1 by 512 by 512 by 3, because the input is always in a batch. Even if it is single image, it should be of batch 1. Okay, now we're gonna output the prediction on the 0th index. Okay, so now I'm going to erase this part. Maybe they confuse you when you look at the code. Okay, so we're gonna say if ypred, so there's a threshold I have told you about already, 0.5. So we're gonna use a threshold of 0.5 to make it a 0 or 1 pixel. Okay, now we're gonna say ypred. Let's preview the shape of the ypred so that it is clear to you what is happening here. So you can see the shape is 512 by 512 by 1. It is okay, it's not a bad shape. Okay, but still we're gonna squeeze it. We're going to squeeze the shape, and let's say ypred. So let's first convert it into integer 32, because here it has converted into a Boolean representation, that's true or false. Now again we're going to print the shape, and we're going to check what has happened by using this squeeze function. Now it will be converted to 512 by 512 only. Okay, so that's the function of squeeze. And from the read mask, I need to remove one line, this line. So now both the read, the original image and the predicted, not the original image, the what we say, the predicted mask and the ground truth mask, both should have the same shape. Okay, calculate the matrix. So first of all, what we're gonna do, we're gonna save the image, all the 3 images, and for that we need to create a function. Let's say saving the images. So first of all, we need a path, save image path. We're gonna say f and quotes results folder. We're gonna save slash the name of the image, and we're gonna say, let's say .png. We're gonna write a function save results. First we're gonna give it the original image, then original mask, then the predicted mask, then save image path. Okay, let's start working on it. Okay, it should be first def keyword should be there. Okay, so what we're gonna do, we're gonna have save the 3 images in a sequence. So it's like original image, then a mask, then predicted mask. Okay, and we're gonna have a separator in between them, a white line, a 10 pixel white line. So we're gonna say line is equals to np.ones horizontal 10 pixel width, and channel is 3, and we're gonna multiply with 255. Now we need to save all the images, so all the images should be of the same shape. Actually they are of the same height and width, but they don't have same channel. Like the image has the 3 channels, the separator line has 3 channels, these 3, but the original mask and the predicted mask don't have 3 channels, so they need to have 3 channels. Okay, so first is ORI, that is ground truth. Expand dimensions ORI in the axis -1. Next we're going to concatenate it 3 times. We're going to say np dot concatenate, then ORI on the axis -1. Okay, and same we need to do with the predicted mask. Let me just rename it quickly, and then we're going to see the result, what has happened with this script. These lines, cat images, basically concatenated images. Np dot concatenate, so we're going to have original image, separator, then we have the original mask, then a separator, and then we have the prediction. Okay, so prediction is basically in 0 and 1 format, so we need to convert it to 255, basically from 0 to 255. So we're going to multiply it with 255, the 0 remains a 0 and the pixel value with 1, convert it to y, that is 255 pixel, and here y pred on the axis 1. Okay, and finally we're going to save it. So we have the save image path, and we have the cat images. So now it should work properly. Now let's run it and check for any issue. Okay, we have, okay, I've written separator here. It should not be here. Okay, in function here, it's not separator, it's line. We call it a separator, but the name of the variable is line. That's my mistake. So let's see what happened now, if there's any issue or anything. Okay, so it's only run once because we have break the loop. So this is the results folder, and okay, here you can see the final result. So here you can see 3 images separated by this separator white line. Okay, this is the original image, second is second image, the middle image is the ground truth, and the third one is the prediction. So you can see we have a nice prediction here. Okay, we cannot say that it's much fine quality, but the on a broad level we can say it's good. How much training I have given into it, so we can say it's really good. Now we need to calculate the matrix. Okay, matrix score. Okay, let's now move to calculate the matrix. To calculate the matrix, first need to flatten the array. Flatten the array. So y is equals to y dot flatten y pred equals to y pred dot flatten. Okay, now we're going to calculate the score. First is the accuracy value. We're going to say accuracy score. The ground truth and the prediction. Second is f1 value. I'm going to say f1 score, ground truth and the prediction, and labels are 0 and 1. Average is binary. And like this we're going to create the jcard, the recall. Let's change the name, jcard score. Next is the recall, and rest all the parameter would remain the same inside these. And like the recall, we have the precision, we have the that is precision. Next is precision. Okay, this is precision. Okay, so now we have the accuracy, F1, Jacquard, recall, and precision. Okay, so now we need to calculate the mean of all the images, individual scores. So let's say we have a variable called score above. Okay, here let's define a variable called score. So we're gonna say score dot append. We're gonna say name of the image. Let's say name, accuracy value, F1 score, then Jacquard score, then recall. Okay, it should not be F1 score, it should be F1 value. Don't confuse. First is name of the image, then accuracy, then F1, then Jacquard, then recall, and at last we have the precision. Precision. What is score value? It should be precision value. What I've done here, I don't know, but by mistake, that's done. Okay, so now we're gonna move out of the loop. First of all, we're gonna remove this break. Okay, so now we're gonna say score equals to what is the real score. So real score is like what we're gonna say. Let's say a loop for s in score s1, because the first we have the name and then we have the scores. Okay, the score is equals to np dot mean score on the axis 1. Okay, so we've calculated the mean roller score. Now we're gonna print the score. Okay, so we're gonna print the accuracy, F1, Jacquard, recall, and precision. So let's run it for now and see if there's any error. I am hoping to have any error, because writing such a long code and then not having any error. Okay, finally we have an error. That's nice. Okay, so we're gonna see what the issue is. Okay, so classification matrix can't handle continuous and binary target. Okay, so I know because the prediction mask is not continuous. It's like 0 and 1, but this original mask should be integer 32. So let's run it now. Okay, it's running. So all the images are also saved and score is also calculating in between. Okay, so you can see we have accuracy of 0.94, F1 of 53, Jacquard of 0.36, recall of 0.89, precision 3. So score is okay. We cannot say it's that good and we can also not say it's that bad. The score is okay. So now how about we can save this score in a file, in a CSV file. So let's do this. We have called the pandas above. Let's import the pandas. And we're going to save in a CSV file. I already have a CSV file here from the previous training and testing. So I'm going to remove it, delete, but don't delete any other file like data CSV and model.h5. So saving, data frame is equals to pd dot data frame. Okay, now we have the list containing all the data and then column names. First with image, then accuracy, then F1, then Jacquard, Next is recall. Next is precision. Now we're gonna say df dot to csv. Save it as a csv file. We call it scores. Score dot csv. Let's again run it. This time a csv file is also going to be saved, containing all the scores, all the individual score of the individual image, so that we can also analyze the score for individual images, where the score is low, where the score is good, because these mean values just give you an overall score, don't give you the image specific things. Let's go to the scores.csv, try to open it. So we have the score for the 20 data sets, 20 images. You can see individual score, so that's much better. You can also see the results for all the 20 test images here. So you can see the predicted mask is okay, but not that best. We can see the fine details are missing in the prediction if we compare it to the ground truth. So you can improve it by giving it by using more data augmentation technique, by training it more, training it on a higher batch size. A little more batch size can also improve the performance maybe. Or you can change the model, like use any pre-trained architecture like VGC16 with a UNET or ResNet 50 or any other architecture. Okay, so that's all about the evaluation part. So in this evaluation part, we have saved the score also, and we have also calculated the matrix. So that's all for this evaluation part. So we have reached the end of this video, and if you are still there, this means you enjoyed the content. So please like this video and share it with your friends. And if you want to watch more videos related to UNET, TensorFlow and image segmentation, image classification, then please subscribe the channel and check out all other videos. And also check the description for the code and other video related stuff. So thank you. Have a nice day.